We're actually going a bit back to basics today to talk about data quality. A lot of people have mentioned it so far. It's always a big struggle, and it's a really important foundation for being able to have a data-driven culture and also building data solutions. So who are we? My name is Gunnhild. I am a data scientist at Statnett, and I've been working in Statnett since 2018. My background is in mathematics and statistics, and before I joined Statnett, I worked in risk analysis and then as an IT consultant in more traditional data warehousing and reporting projects.
My name is Alexandra. I just finished off my 18 months traineeship at Statnett. Currently, I am working as a power system engineer, also at Statnett. But as a trainee, I had the pleasure of working in 3 different departments, one of them being the data science department. And I still work with some of the projects that I work with there, including the one we are talking about today.
Yep. So today we are first giving a little introduction about how the power grid is balanced. And then we're going to give you a little pep talk about data quality, although I'm sure a lot of you realize the importance of it already. And then we'll dive into the solution that we are working on building now in Statnett for monitoring data quality and the reasoning behind our approach.
So Statnett is the Norwegian transmission system operator, and we operate around 11,000 kilometers of high voltage power lines, 166 substations, and 1,400 kilometers of subsea and land cables. We are responsible for interconnectors to Sweden, Finland, Russia, Germany, Denmark, and the Netherlands. And we are responsible for balancing the Norwegian power system. What does that mean? At each given time, the electricity demand from electric cars, industry, and from us as regular citizens needs to be met by equal electricity supply. Production from wind power plants, hydropower, and other production units. This balance between demand and supply is supervised at all times by operators at our National Control Center. If the demand is larger than the supply, these operators need to regulate the balance, activating more production. If there is less demand than supply, it's the other way around. And this process today, the process of balancing the power system, is mostly manual. But the power system and markets are changing. The time resolutions of the energy and reserve markets are about to change from 1-hour settlement period to a 15-minute settlement period. Our production mix is changing. The future will have less controllable energy sources and more variable renewable energy as wind and solar power. And the Nordic power system is getting increasingly interconnected with the European power system. And all of these changes and more with them are making the task of balancing the power system harder.
Yeah, and in fact, we think that the need for balancing will be larger and it will need to be acted on more frequently. So this cannot be done manually by the operators anymore. So therefore, we are automating the balancing operation. And to do this, we make a forecast of the imbalance. And this tells us how many megawatts we are from a balanced system. Now, this forecast is based on market data, such as production plans for wind power, calendar variables, such as the hour of the day or the minute of the hour, and power system observations, such as the measured flow on power lines and the observed imbalance. And this imbalance forecast, sorry, I'm going a bit ahead with my animations here. So now we're back with the imbalance forecast, which is updated every 5 minutes. And here comes the request for how many megawatts of regulating power we require for the next 15-minute operational period. So when we have done this, updated our imbalance forecast, this is then made into a request for regulating power, how many megawatts we need for the 15 minutes operational period. And this is then sent to a Nordic optimization All of the Nordic transmission system operators do this, and the optimization is across the Nordics. Now, there are a lot of cool machine learning algorithms and optimization problems here, but today we want to go back to the good old-fashioned data quality.
So let's talk through an example of what kind of data and data quality issues we can have in Statnett. All over the power grid, there are sensors measuring and collecting data that are used to monitor the power system in the present. This data from the sensors are now also being used in new ways as input data to the machine learning algorithm that Gunnhild described. And this machine learning algorithm delivers a forecast that serves as input to the request deciding how we should change production or consumption. It helps us balance the power system. So we need confidence in the quality of the data that this sensor is delivering, not only because it is important for the continuously monitoring of the power system, but because this data may affect how we balance the system. So what can it look like if we have a malfunctioning sensor delivering data? This first screenshot here shows measured flow of power between two different areas in Norway. On the y-axis, there is megawatts, on the x-axis, time. And here the data is having the expected profile. All the sensors measuring flow that accumulates to this total flow between the areas are working correctly. But let's see a screenshot for the measured flow between two other areas in Norway at the same time. This looks a lot different. There are oscillations in the data, and these oscillations were caused by one malfunctioning sensor on that corridor. This one sensor affects the data greatly. And we need to know if this is happening. And we need to know if a sensor is delivering bad data, like here, or no data at all. And not only that, we also need to be able to handle it if it occurs. The system must be robust.
Yep. And data quality is not only important for the predictions that we deliver online, but also for our model performance. So we need the quality of our training data as well to be as good as possible. And we have seen 5 times improvements in our model performance when we have corrected training data versus just hyperparameter tuning the same model. So this is really something we need to get right in order to deliver the best possible models. But it's not only the model performance that suffers if we have bad data quality. Lack of trust in the data also erodes trust in the results from analysis and decisions based on data. And the first thing operators want to know when they are deciding whether or not to trust a forecast is what data it was based on. They want to see the model's input data and to check if something here is completely off. So what do we do? Well, you might have heard people in information security and software development talking about shifting quality work left, meaning that you should start testing and security work early in the development process. And in fact, that this is key to being able to do meaningful work on testing and security, to be able to catch vulnerabilities or bugs before they're built into your system. And it can be quite difficult to patch together a fix for these kinds of problems on a finished product. The solution is often that the teams should be unable to do this work themselves, either through guidelines or best practices or auditing tools. And I think this also applies to data quality work. So this is what we're working towards, a solution that enables data quality monitoring to be set up as simple as possible with a little configuration, so that both I, as a data scientist, and Alexandra, as a power system engineer, can understand the current quality of the data that we have. So what we're doing is building a pipeline for data quality monitoring with the Python library Great Expectations as the main component. And Great Expectations introduce they have a lot of good selling points. So here, one of them, I've copied this from their documentation: make implicit knowledge explicit with unit tests for your data. And all the Pythonistas out there know that explicit is better than implicit. So let's go through some of these concepts that Great Expectations introduce. First, our expectation suite. These are the expectations that we have to a data source. or the requirements we have to them. So in this example, we expect the measured flow column to be between minus 2,200 and 2,200, and this is in megawatts. And we expect it to be between these minimum and maximum values 95% of the time. And this is where a power system engineer can make their implicit knowledge explicit. These minimum and maximum values here are based on the capacities for a corridor, for the different lines in a corridor, and the flow can go in both directions, so it could be both negative and positive. And this capacity is not a physical limit, so there could be shorter periods of time where we see larger values or values outside of this band. So that's where the 95% comes in. So now the power system engineer has taken some of their knowledge and shared it with us in their expectation. And then we can see a validation result if we run the expectation suite. So here we can see the test results of our unit tests for our data, one successful test and one failed test. Now there are some benefits to using Great Expectations. We have a large built-in suite of expectations, but it's also extendable with custom expectations. And there's also a built-in suite of data source connectors. The philosophy in Great Expectations is to take the compute to the data. This is perhaps a bit different than other libraries, so Great Expectations require a data source connector to be specified. So what we saw initially was that not all of our data sources were supported, so we're actually working on a contribution to the library to add the support that we need. So that's something that we're quite proud of, that we're able to contribute to open source software. There are some drawbacks with Great Expectations as well. It's under relatively rapid development. Some experimental features could have breaking changes from time to time. The core components are more stable though. Documentation is perhaps not the best. But we found that it works quite well for our initial work on this pipeline. So let's take a look at what the process is today. It starts with a data steward, and this data steward is a formal role in Statnett for a subject matter expert. And this is someone who knows the domain well. They're responsible for following up the data quality, and they know what expectations to set to the data. So we have data stewards for some, but not all domain areas in Statnett. And in our first iteration of this monitoring tool, the workflow is as follows. The data steward creates an expectation suite in a Jupyter notebook. And we imagine that this is kind of an iterative process where they explore some of the historic data and try to run some expectations against it. And when they have found an expectation suite that they are satisfied with, they save it. After saving it, the data steward schedules how frequently the expectation suite should run and what batch size it should run on each time. For example, you could validate 1 day of data, validate 1 week of data every day. You can choose whatever you like. And when the validation results are run, the data documentation is updated. So the saving of validation schedule triggers reconfiguration of the application that actually runs the validation. So this happens automatically when the validation schedule is saved by the data steward. The results are saved in a database and summarized as HTML. And for now, we serve this as a static website with which holds the data documentation. And the screenshot on the previous slide was from this data documentation. And the final step, if any of the validations fail, each failed validation generates a GitLab issue assigned to the data steward. So then the data steward needs to act, either find the cause of poor data quality, perhaps there's a malfunctioning sensor as we saw earlier, and they need to schedule a calibration or replacement of that, or possibly they need to revisit the expectation suite. So this is what it looks like in our first iteration, and we haven't found any blocking issues with our methodology so far, but we're considering some changes to make this a bit more smooth. When the data steward has to create the expectation suite in a Jupyter notebook, that requires that they are able to work their way around the Jupyter notebook or know someone who can help them. Luckily, Alexandra is a super user of this monitoring tool, so she can help anyone who needs help. But we're also considering moving this to another user interface and making this first and second step a bit more connected, and instead of having two separate interfaces. We're also considering integrating the validation results from the validation runs in other monitoring solutions. The results are stored in a database and the HTML is stored, so we could serve the results in some other monitoring application. But for first iteration, this workflow proved that our monitoring tool could work.
And why do we believe in this approach? It clearly defines and allocates the responsibility of data quality. Each dataset is to be assigned a data steward. This is a work in progress, and we're not there yet, but that's the idea. And the data steward is responsible to follow up on the data quality of the dataset. This responsibility includes following up on the issues made in the grade expectation workflow. And the data steward must take action if the quality of the dataset is not good enough. And as Gunnhild said, the dataset is not randomly assigned to any data steward, but to data stewards with specific domain knowledge within the field that the data is describing. The people who know the data is also working with the quality of it. And the next is that we get one common solution for monitoring data quality across all domains in Statnett. Instead of each team or department handling it in its own way with their own data cleaning scripts or in other programs like Excel, we will define one data quality monitoring pipeline that can be used by everyone. And last but not least, this solution automatically generates documentation of the data quality of each tested data set. This documentation is available for those who may need to see it being a data scientist or an analyst. So to summarize, the responsibility of data quality is clearly defined and allocated. There is one common solution for data quality monitoring across the company, and our knowledge of our own data quality is documented and available for those who would like to see it.
So that is what the process looks like today. If you have experiences with setting up the same thing or perhaps different data quality monitoring libraries, we would love to hear it. And if you want to work with us, we also have, we're looking for a Python developer to join my team. You can find several other developer positions on Statnett. Thank you.
Thank you.